Hello everyone. Guys, you can hear me? Hello.
Yes, sir.
I can hear you.
Yeah. Okay, Godfrey, I can't hear you though. But anyways, yeah. So
You can't hear me?
guys, we'll have to wait for
Hello?
another 5 to 7 minutes. We have all participants joining in. So once everybody joins, we will get started. So I can see a lot of people signing in right now. A number of attendees is kind of growing. And please know this is a webinar, so it's going to be a broadcast kind of communication. So from the panelist, we are going to do most of the talking, and you guys will have to, if you have any questions, you can chat in and put in a question there. So let me just wait for some more people to join, and then I'll get the session started.
Asif, can you hear me?
No, Godfrey, no.
Oh, you can't hear me.
Godfrey, I can't hear you.
Okay, let me log out and log in. Okay.
Okay, wait. Yeah. Hello.
Asif, can you hear me?
Yeah, yeah.
Oh, okay, great. I think someone has to enable me sharing screen actually. Host disabled participant.
Okay, I can do that. Yeah. Godfrey, can you share the screen now?
Yes, I can. Okay. So Asif, you can hear me still?
Yes, yes.
Okay.
So I can see people signing up. Yeah. See more and more attendees coming.
if we can start, maybe.
Yeah.
Also others
Okay.
are waiting, right?
So, good afternoon, everyone. This is Asif here. I'm the host for the evening, and welcome to the webinar series from Prodigy. So today's topic we are having is called debugging embedded designs, and with me I have got Godfrey. Godfrey has got more than 25 years of experience in test and measurement. He was working with Tektronix and Agilent HP, and he's the what do you call founder and CEO of Prodigy Technovations. And Prodigy Technovations has been creating world-class products on I2C, SPI protocol analyzers, as well as I3C and UMC as well. So welcome to the webinar series. So a couple of rules before I get started. One thing is, if you have any questions, what you will have to do is you will have to type in your questions in the Q&A tab. So everybody on your right, what do you call it, the bottom half of your screen, you will see a Q&A tab. If you've attended a lot of Zoom meetings, I think it should be fine with it. So just go to the Q&A tab, ask your questions, and what we will do is we will pick up your questions and start answering one by one. That's one thing. Second thing is this session is going to be recorded. So in case some of you have missed the sessions, we are going to even email it to you. And yeah, I think we are seeing a lot of more people joining here. So this session is going to be totally for roughly 1 hour. First 45 minutes, what we're going to do is we're going to have the presentation, and the last 15 minutes is going to be the Q&A session. Okay. So now I'm handing over to Godfrey. Godfrey, you can take it forward from here. So I'm going to stop my video and I'll hand over the session to you. You can take it forward from there. Thank you.
Thank you, Asif. Good afternoon, everyone. Thanks for the nice introduction, Asif. Just to, again, my name is Godfrey Coelho. So I'm going to speak for next 45 to 60 minutes about the debugging embedded designs, and I would like to make this more interactive. You can share your questions. In between, I will take a look at if there are any questions, so I can get back to you. Okay. So just feel free to ask any questions, so that we would like to hear more from you. So what is the agenda today is we will be basically how does people go on doing a embedded designs flow normally, and debugging embedded designs, like things like during the hardware bring up and software and hardware integration. So we feel that's the most two critical parts. If these two activities go well, rest of the activities are kind of like not taken care, so we can have a good product in the right time. So then we will introduce a product which will enables you to debug these designs. That's a Discovery Series Logic Analyzer, and followed by a brief demo of this product, so that you get to know what all you can do and how easy to use this product. So that's the agenda, and of course there will be a question and answer. So we like to hear more. We like to have more questions from you actually. So introduction is that, like if you look at any embedded system, right, it will, like I've taken a very simple example here, Arduino board. It will have a microcontroller and many IOs like I2C, SPI, UART, and there will be a software running inside. So you need to debug at the hardware level, system level, and once you deliver the product to the customer, you have to provide the support. There may be some things are not working, and these are all the critical requirements in embedded designs. Now, that's what is the embedded market as such, if you really look at it, right? So it's a very wide and very large market. I'm not going to get into the numbers here, but just to give an idea, embedded market consists of industrial automation, home automation, medical and healthcare, lighting, motion controls, white goods, metering, power tools, consumer electronics. So it's a very wide market. So it's a lot of people to deliver a lot of simple products. So complicated products, you need to have a good tool which enables you to debug the products and provide a good consumer satisfaction. Because most of the products, if you really look at it, they are targeted to the consumer market, and consumer satisfaction is a very, very critical in case of a winning the customer repeat orders, repeat business. And in order to have a good product, the product has to be tested thoroughly, the product should be reliable, and the product should be having enough design margins. So these are some of the important parameters when it comes to the embedded market, and mainly targeting to the consumer segment. So the design flow, if you look at it, right, normally you start with a system level requirement where you start writing, okay, what is the requirement? What are the capabilities are required in the product, right? So one can say that motor should run at a maximum of 2000 RPM, then it should start having a control variability of 100 RPM to 2000 RPM at a resolution of fine numbers. So that's a system level requirement someone can write down. And from the system level requirement, now how to achieve that, right? When it comes down, you start writing low level requirements, we call it. Low level requirements is like, okay, now in order to do that 2000, okay, now what is the resolutions we need? What kind of a, like how fast it should switch the resolutions? These are all low level requirements. Then once you write down the low level requirements, normally system level requirements will come from the marketing team or from the consumer side, and the low level requirements are derived out of the system level requirement. And from these low level requirement, then you start the hardware team and the software team sits together and then trying to come up to a plan that what should be, we should put it on the hardware and what we should have it in the software. So these are the two partitioning takes place, and from there we will have a hardware level requirement and then a system level requirement. So that's the kind of, you get into like, no, sorry, hardware level requirement and software level requirement. Then you will have a two teams working independently almost for some time, developing the hardware design and making the assembly of the board, everything. Okay. So that takes, like, you start with identifying the components, what are the right components to meet the requirement, and how do you put them together, making the schematic, and then how to maintain the signal integrity, the board. And when you do all these things, you also keep cost of the design in mind, how much is going to cost to manufacture these kind of products. So you will look at all these things, and end of the day, you will have the board coming back, which is assembled, and then you need to do the power on of the board. On the other end, the software team, which does the software architecture and start developing the software. And they would, before they have the hardware, they will do all kinds of simulations or maybe unit level testing and debugging. Without the hardware, they will try to do as much as the development work. And once we have both the hardware and software, this needs to be integrated, and the hardware software integration takes place. And when it takes place, nothing works smooth. Actually, let's be honest that no, there will be a lot of challenges, a lot of issues, and both the teams may be trying to complain each other and trying to say the problem is in the software, problem is in the hardware. How we go about debugging this? No, how do we, like, it's a challenge for the program manager many times how to moderate between these two teams and making sure end of the day the problems are resolved. And once things have started working, we have to do the system level testing, because end of the end of the development of the cycle, the product has to meet the system level requirements. So one has to test the product, how far it meets the system level requirement, is everything is covered, what additional features we may have it, everything. So once the system level is testing, the product will be then be rolled out for product launch. So this is a very, in my opinion, a simple, closest design flow I can put together for an embedded design, which most of the industry is following, so that you can have a parallel development of the hardware and software and a seamless design flow. Now, here is a typical picture just to give you some idea how does a embedded system would look like. You will have a microcontroller, which may be from Texas Instruments or ST or Microsemi, or from so many different Intel or Qualcomm. It can be from different vendors. Okay, so you have something which is normally microcontroller is associated, maybe a heart of the embedded system in terms of hardware. So that's what it is. And then the people or the design will connect to different sensors
different peripherals to the microcontroller and to the system to develop this, to deliver the system level requirements. And now this interface between the peripheral devices and memory, all those things takes place using different interfaces. Some of the most commonly used interfaces are I2C, SPI, and UART. There are some new interfaces that are coming up, which are much more being driven by performance and maybe low power consumptions and all those things. But most commonly used are I2C, SPI, and UART. So this is how a simple a system level how design would look like for a patient monitoring design. Okay. So this is a reference design. We are taken it from Texas Instruments website. Now, then once we have the board design, right, now we know what is the flow and how the system looks like. Now, the hardware design is done, schematic is done, board level, the layout is done. We got the PCB fabricated and board got assembled. It comes back to the lab. And once comes back to the lab, now there is a certain process the hardware design team follows. That is a board bring up process. So one of the things which is very, very important is that to make sure we don't burn the board or we don't damage the design. So first thing is that we'll try to power on one by one power supplies. There may be an input of 12 volt DC or maybe some other voltage levels. So we'll try to see whether the input voltages are perfectly fine. All the voltage modules are working fine one by one. We will try to make sure that everything is working fine. Then the power sequencing. Sometimes, or many of the designs, you need to turn on certain voltages ahead of some time. The second one should come later on after certain time. So there is a sequence of power turn on activity should happen, and for the successful operation of the board. And so in order to make sure that you need to characterize the power sequence is working very well and everything is working good. Okay. Now, next level of debugging is that all the digital components on the board, they are all able to communicate as per the requirement. Now, in order to ensure there is a good level of operations with all the digital circuits, so you need to ensure that all the setup and hold times are within the specifications, are as expected on the board. So there in a synchronous system, there will be a clock. The clock source has to be clean and should be able to drive all the digital circuits, and all the setup and hold times are in good shape. So all those things we have to take care of that. Then how good is the design? Is there any glitches? Is there any runs? So because if those kind of glitches are present, so we know that once we have our software integrated to the hardware, these glitches will create problems in the design when the system or when you're trying to bring up the software and hardware together. So we need to clean up all those glitches and make sure the hardware is working fine. So one of the methods of checking the all the digital ICs, everything is that trying to do a loopback test or trying to make sure that to feed some reference signal from the function generator to the input of the ADC and make sure ADC is giving the proper outputs and take those data, capture it maybe in a different tool and analyze it. That's where the testing equipment becomes very, very handy and very useful. If you have a very high-speed designs in embedded, for example, maybe you have a HDMI or nowadays the D5, CSI, MEP signals are very common. So you need to make sure that these high-speed signals are pretty reliable. The signal integrity is maintained, and so you have to do an eye diagram analysis. Maybe you have to again do some loop back prior to having some external devices, because we need to remove the ambiguity in the design. Because if you use some of the actual product, in the bringing up the board, then we may not be knowing whether it is in the component we have selected or is in the board problem. So we need to have a reference source, which many times can be loopback or from a generator, provide the known source of signal to the board and make sure that the signal integrity, everything, eye diagram, jitter, all those parameters are maintained within the spec so that the board is completely working and powered up. Okay. So that's the normal board bring up process. And there can be a lot of issues. It's not that directly it's going to work. Sometimes people spend weeks together in bringing up the board to make sure everything works fine. Now coming to the hardware software integration, like the people have done software architecture development, unit level is testing, and then you have a software, and that software you have to integrate with the hardware. Normally you connect the software development environment to hardware using different interfaces. It could be USB, or it could be flash, or it could be USB or JTAG, whatever. So you can program the flash, and then debugging the software operation takes place. So this is one of the examples where we are trying to do some ST microelectronic development environment. We are trying to flash the program, select the flash, download the program, and it starts debugging. So one of the first step people do in the software, when you have a software running in the system and the hardware integrated through the programming interface, so you start doing the single stepping. Basically, single step enables you to look at how the code is executing, what is the input to the code, that particular line of code, and what is the output. Is it as per expectations? So you do that by doing the single stepping and trying to go through that entire code over a long period of time. So that's how you start doing the debugging. So that's the kind of you start developing the software and trying to integrate that. And here is an example where we can see that we are trying to write a certain number of data to the particular location using the development environment during the single stepping. And we can see here the red numbers, which is data which is present there in the software, is being written. And at the time, at the right location, nothing is present. Once the activity is completed, and we can see the data is present at those locations. So this is a debugging normal environment where it you can see. But this is when everything works fine, right? So if there is a problem, if there are glitches on the line, how do you try to see that? That is a challenge. Okay. Now you have a low cost tools like for I2C, where you connect the I2C bus over here and try to see the signals and what is the data is going on. You can go and see on this low cost small kind of tools. Okay. But here the data is good, then you can see everything is working fine. If things are not working so well, then you may start seeing the data which is corrupted, or you may miss the data. Then there is no way you can get a visibility what is going on, right? The most important part of the embedded design is the visibility. So if you don't have a visibility, we can really cannot see where is the problem and how to isolate the problem. That's where I think the Prodigy Discovery Series Logic Analyzer becomes a very, very important role it plays. Now, in this slide, we are just showing one example before we go into the actual product introduction. We are capturing a I2C traffic on the bus, and we also simultaneously show the decode, and in the decode, we'll show the timestamp, what's the address value, data value, whether it's acknowledgement, NAC, or any errors that it will report. And it also report the frequency of operation, at what data rate it is operating. Now, what you see is interesting here is that most of the protocol analyzers, they will show you the data with respect to the clock, what is going on the line. Now, in case of a Discovery Series Logic Analyzer from Prodigy, we can show you the glitches, like, there is a small data transfer which is happening between these two clock cycles. Now, in this example, it is actually not on the edge. Actually, it's between the clock cycle, may not affect your design. But if it comes at the rising edge of the clock, this kind of glitches, because the glitches are unpredictable. They may come at any time. It's kind of a noise, right? Noise is something we don't know, cannot define when it comes, when it cannot. It's a very random in nature. So these kind of glitches, if they come at the rising edge of the clock, and then it will corrupt the data. So it's very, very important to look at this kind of information if it is present on the data lines of the clock line. Now, in this slide, we can see that the glitches which are causing the data to NAC, end of the day, you get some wrong data. So the master will start giving the NAC, not acknowledgement. And also the Discovery Series Logic Analyzer, If the data format of I2C is not as per the specification, it will start throwing out the error message for the developers, so that you know there is something wrong. Now you have to go and fix it. Okay, so you get a good visibility to your design at a very, very low level. That is, you get to see the protocol layer information, then you can get to see the waveforms of the clock and data, so that you can exactly know that exactly where is the problem, and you can go back and forward looking on this data and trying to identify what might be the cause of the problem. Okay, so you can do a complete debugging of the embedded systems in some of the cases. Now, solution to the embedded problems is that, like, most of the problems are at a system level. That's what, when we did the market research, we can identify that 75% of the defects are identified at the hardware software integration and the software. The kind of tools people would like to see at that time is that you need a logic analyzer, and then you like to see some clock and voltage regulation. Maybe you need some other test equipment, JTAG debugging tools, and functional RTL simulation. Sometimes if you're working on FPGA, you may need it. So you are looking for a different solutions to your embedded problems. Now, some of the solutions to your problems are like simulation tools, which is in the early design cycle, they have it. Normally you have access. You need an oscilloscope to look at all some of the signals between the setup and hold time kind of information, and maybe a logic analyzer, which is do some digital debugging for you. And then you need a protocol analyzer. Like if you have a multiple different protocols in your embedded system, you need each protocol for I2C, SPI, UART, or some other interfaces. So all these kind of different tools are required to do the timing analysis, logic analysis, and protocol analysis. Okay. So these are the tools which are required for a good embedded design purpose. And what we need is an oscilloscope, as I mentioned, logic analyzer, and the protocol analyzer. So these digital channels and the protocol decoding software, they will all needs to be like, is a very handy requirements. Now, what is Prodigy solution is that we are offering a logic analyzer with a protocol analyzer, which is a combined tool, which enables you to do the faster debug at times. So it can reduce your development cycle, and also it can give you a system level insight. Okay. So what I will talk about that system level insight in coming up slides, because normally, like, we may be looking at one activity, but in a system level, everything working in a tandem. It's like a human being, right? Our eyes will see something, and then our brain will process what we saw in the image, and then we'll take some actions using hands or some other action. So we'll take it. So these are all synchronized activities. So embedded system is something like anything. It can read the data. Based on the data it has come in, it can process the data and take the action in a different interface, and there is certain time frame involved in that now. And you look at the system level activity, you really need to correlate all these activities together, so that to identify what is the nature of the problem. Okay. So what we have is that we have a logic analyzer. That's a Discovery series logic analyzer which we are talking about. We are one of the industry fastest sampling logic analyzer at this time. So it's a 1 giga samples timing analysis on a PC based small logic analyzer. You have high-end logic analyzer, which is a modular. They go faster, but they are also very, very expensive. They cost more than 20,000 US dollars. But this logic analyzer is very simple in nature, but it provides a very high sample rate of 1 giga samples per second timing analysis. It can also do 100 megahertz state analysis. The state analysis, what's the difference between time and state analysis? Timing analysis is something you look at the signal using the internal clock of the logic analyzer. You sample the signal at a very, very high sample rate, so that you can get to see the resolutions, and if there are glitches, everything you can see. The state analysis, we are trying to see the signal with respect to the clock system clock, that is a devotee's clock, so that when the clock transition is happening, what is that data is going on the bus, we can see that.
So then you need to look at we provide I2C, UART, SPI protocol decoding is supported with this product. And also you can do a triggering on those packet content. And one of the most unique feature of this product is that it can do a simultaneously decoding of I2C and SPI and UART. Okay, the simultaneous decoding of I2C, SPI and UART that enables you to look at the system level performance. What I said was that the system level is that if the data comes into this processor and it gets processed, like data may come in using the SPI interface, it gets processed and it needs certain amount of time. And based on that, the processing of the data, it can take some action, and that action is going to be available on the I2C bus or a UART bus. And then you can see when the data is coming in, when that action is going out, and how much time it has taken for the input and output activity, and then is it really meeting the timing requirement? Is it as per the expectation? Or do we have enough margin there? So all those things, so multiple repetitive tests one can run, and you can characterize the entire performance at a very, very low level using this Prodigy developed Discovery Series logic analyzer. It has a state-of-the-art GUI. It's very easy to use it. I will discuss that later. And one of the things which many people ask for is how much I can capture, because that's a frustration, right? Because most of the debugging tools which is available in the market, they have a very shallow depth. They can capture it for a very, very short period of time, okay? Maybe a few megabytes of data. But in case of a Prodigy Discovery Series logic analyzer, you can capture the data for, okay, there are, I think the questions which were there, I don't see them now, okay? Sorry for the interruption. So there was some glitch here, and let me continue with the demo. Okay, so I think here is a demo like where I'm showing you now a small video. So this is a screen which you get it where I can first connect with the hardware. The device gets connected. Then I can decide whether what mode of operation, LA plus PM mode or a PM mode or a LA mode, okay? So depending on the selection, these menus will change. And here we have a setup and LAPA mode, which is like enables you to select the sample rate. Right now, I'm going to do a timing analysis, LA mode. The state and timing analysis I can look at, okay? And then I can do the state analysis, timing analysis, I can select the sample rate and I can select the number of channels. Now in this case, I have connected all the 10 channels. And then I can select the voltage levels of my signal. We can start from 1.2 volt to 5 volt. In this case, my DUT, which is at around 2.5 volt. And we can keep running on that, select that. Once we have the selections, so we can go to the trigger menu and select the trigger. So we have a auto or a pattern trigger for timing analysis. So we can enter the pattern. So in this case, I'm going to use the auto, and then I'll just say acquire button, click on the acquire. Okay, so once we click on the acquire, you get this window where on the top we'll show you the acquire duration, how much data it is captured. Okay, the full waveform. Out of that, only the small sliding window data is displayed on the screen. Okay, you can see all the timing waveforms, timestamp. You can have cursors. So I can move this sliding bar anywhere in this graph. So right now we are captured almost around 14 seconds of data. So while it is displaying, the acquisition continues to happen. Now, in case I want to analyze some data, I can do a zoom out and zoom in, and can have markers. I can place the markers. So I would like to know the timing between this clock, the channel 1, and rest of the data transition. So I can do that. Okay. So I can also right now sampling at 125 mega sample. Okay. So now I will place the cursors at this window. And then we can have, let me go back and place the cursor in when there is a rising edge of the clock. Okay. And then I can further zoom out and place the cursors more accurately. And yeah, so I can easily move it. So now the zoom is not sufficient enough. Maybe I can zoom further. And then I can place the cursors more accurately and measure the timing. So we can see here it can be varying somewhere around 22 nanosecond between two edges, whatever I want to make analysis. Now same data I can go and further analyze it. I just change the sample rate to 1 giga sample, and we will capture the data again. And you can see the plot is going on and the acquisition also going on at the same time. It's capturing 6 seconds of data. It's continue to capture, okay? So whenever I want to stop, I can click on the stop button, and then it stops the acquisition. So we captured around 14 seconds of data. Now at this edge, what's going on, right? We want to zoom out in that area. So one of the good part is that the level of zoom out we can go to the very, very fine, and we can place the cursors more accurately. And then we can analyze how the setup and hold time or digital timing information, everything we can look at in detail. So here the signals are sampled with respect to the clock, which is internal to the logic analyzer. So the maximum sample we can get a resolution is 1 nanosecond, that is 1 giga samples per second, which also enables you to capture the glitches, okay? So in case you want to capture some glitches, we can also see that. Now, let me scroll a little bit forward. So I just clicked on, I think, again, capturing the same information. Now we can see glitches on the channel 10. So you can see this transition. So with the high sample rate, you can now able to see the glitches. And once we have the glitch capture, we may like to see what's the width of those glitches, so that we can trying to estimate what must be causing those glitches. So we can keep the markers or cursors, and we can know the delta. Okay. So this is more of a timing analysis, what we are doing it. So please send in your questions. It's important that if you have any doubts, you can ask, so we can have a more interactive session. Okay, so again, you can see captured for a long period of time. 13 seconds is very, very fast. I have a lot of data, and we can actually capture it for timing analysis for quite a longer period of time. Okay. Now let's go and do a state analysis. What I'm doing, we can use 2 clock DVTs, but in this case, I'm going to use a 1 clock source from the DVT. It's connected to channel 1. And now with respect to the channel 1 rising edge, we have selected rising edge. With respect to that, we will see what is happening on channel 2 to channel 9. It's actually a counter, okay? We can see that it has captured the data. We can also see the clock here, clock source, and then channel 9 to channel 9 data lines. Now here is a bus information, like it will tell you at each clock edge what is the data counter is incrementing. Like now, I just move the sliding window somewhere around 5 seconds, just for my convenient, okay? And I'm trying to move into some area for a demo purpose, and let me just zoom out here. Sorry, okay, I was trying to do a pan, but entire data is on the screen. So yeah, so we need to zoom out here actually. So let me just zoom out, and I can see some glitches here, and how these glitches are affecting my counter, right? So one of the important thing is that in at 100 megahertz, we are able to, like, with respect to this clock, we are able to see the these kind of sudden glitches. And we can see here, unfortunately, this glitch is happening at the rising edge of this clock. Okay, so you can see here, and that causing the counter to jump suddenly. Okay, and then come back. So these kind of problems, which you can easily track it using Discovery Series logic analyzer.
So yeah, that is the state analysis which we talked about, like in the logic analyzer mode. Let's go to the protocol decoding. We will do a simultaneous decoding of I2C, SPI, and UART protocol decoding. Okay, so I connected all the 4 lines of SPI, clock and data. The UART data rate is around 34,800 baud rate, and then the signal amplitude remains same. I just go and just say acquire. You can see there is a picture which is like a running picture, and it will start plotting the clock and MOSI and data. So now you can see simultaneously what is going on in I2C, SPI, UART, and I2C bus. Okay. So separately we can list them I2C activity, SPI, and UART. You click on the I2C bus, and then the waveform corresponding to that will be highlighted here. We can also do a zoom in, zoom out, and you can see more data out here. And you can see SPI data comes it initially, and then I2C UART is continue to send some data. So yeah. So you have a bus diagram which will give you information about what is the data is present in MOS and MOSO. So you can go and do a debugging. So we have captured almost around some 70 seconds of data. While we are acquiring and analyzing, the hardware protocol analyzer keep acquiring the data, and software at the background is decoding and updating. Let's do some decoding. Trigger on a I2C bus, like we can trigger on SPI content or a UART content or a I2C. So in I2C, we can trigger on start, address, all those things. Let me trigger on I2C address 46, and we can at a write active operation address, okay? And they just say acquire. So you can see here it's waiting for a trigger. When the trigger is found, then it will tell you trigger is found, and it will start updating the screen at the same time. And you can see your trigger event happens at, and it's marked as a T. And the timestamp is at reset there at minus, and then it's a positive and negative. You can see pre-trigger and post-trigger data, and you can select that packet, and you can see the waveforms, and you can correlate all kinds of activity. So this is the overall actually complete information kind of demo of Discovery Series Logic Analyzer. We can do a pan, you can scroll, and we can also go and generate a report in PDF format. So I think now I can take some questions if somebody has a question, because we have another 10 minutes to go.
Yeah, so Godfrey, let me ask some of the questions, right? So, which I've received. So, basically, how many channels are supported in this logic analyzer?
So currently this channel is supporting 10 channels, okay, and all 10 channels you can sample at 1 giga samples per second, okay, and you can also reduce the sampling rate. In this class of product, right, it is a portable logic analyzer which is a USB interface. This is the highest sampling rate available in the industry at this price point, okay, and it provides a very long acquisition capture. So just to, that's response to your question. Just to stop that, so we generated report. In the meantime, I'm going to, like, there's a lot of data, so I'm going to open the PDF file, and you can see all this configuration information. You can look at the setup information. So you and all the packets, everything you can see it here. So that's about the complete report generation capability, everything. Okay. And I think in this file I'm generating, I didn't have an Acrobat, so it was giving something. So that's overall, Asif, response to a question. We have a 10 channels at 1 giga samples per second, and and it can capture for a long period of time, and it can offer you one of the industry best trigger capabilities.
There's another question coming up. So basically, what are the other interfaces like other than I2 CSP and UART supported in this logic analyzer?
Yeah, currently we are available I2 CSPA UART, but I think in a very short time, in another 1 month, we'll be announcing I3C, RFFE, and SPMI. So those who want, they can go ahead and invest on this product, and they should be able to upgrade their hardware to I3C, SPMI, and RFFE, which are MIPI protocols, very commonly used in automotive electronics in nowadays, apart from mobile devices. Okay, so yeah, so that's going to be available very soon, Asif.
And can I trigger on a pulse width?
Of course, you can trigger on a pulse width. So there is a positive going and negative going pulse width trigger capabilities are available. You can say less than 5 nanosecond, greater than 5 nanosecond. So you can trigger on such events. Yeah.
Okay. So people, if you have more questions, you can kind of type in your questions on the Q&A tab. I see one, one more hand raised. So any more questions here?
Yeah, the question I can see here is, let me read out this question. Is this powered by only USB? Yes, it is powered by USB, but we are also giving a 12-volt DC adapter in case, if the USB has some trouble. But we recommend to use a 12-volt DC adapter, which we provide it with the unit. So
I think that's all questions, Godfrey. I think
yeah,
there's one more question. How many USB ports will it support?
For this protocol analyzer, we need only one port, so that's good enough. Actually, we don't need more ports because it has a USB 3.0. So you just connect to the software to the computer. You don't need more than one port.
Yeah.
Yeah.
Yeah. So if you further have any questions, what you can do is you can email us at contact@prodigytechno.com. So I think Godfrey is displaying the slide there. You can see. So any further queries, you can send us an email at contact@prodigytechno.com. We'll be happy to answer, and we'll also have a recorded sessions of this available so that you guys can go through it and let us know if you have any further questions. I think
Yeah. Thank you. Thanks for your time. Yeah. And there is some glitch, I think. Sorry for that. I will make sure next time it doesn't repeat.
okay.
Yeah. Bye
Thanks,
now.
Godfrey. Thanks for your
Thank
time, and thanks everyone for joining the session. And hope to see you next time in some of the other seminars which we have. Thank you.